is a state variable that satisfies a differential equation that I'm writing here in this very abstract form. So y could be the pressure field, for example, in the wave equation, or it could be some of the fluid mechanics for that optimal control problem. Again, so I'm interested in the forward problem, numerical methods, specifically for wave propagation problems, energy conservation, discretization. So when you solve these problems numerically, you have the choice of using several methods, or even developing one yourself. And aside from accuracy conditions and convergence and these sort of mathematical ideas you want to keep in mind, maybe you also want your numerical method to satisfy something physical that the physical problem satisfies. So if the physical problem is energy conservative, then maybe you want to preserve energy in a discrete sense in the numerical method. And a generalization of energy conservation is entropy conservation for nonlinear wave problems. In inverse problems, I'm interested in efficient regularization schemes for large-scale problems. So a lot of these problems are not just ill-posed, but perhaps even ill-conditioned, meaning that the mapping from control variable or the median parameters you're solving for to the state variable y could be an ill-conditioned mapping, meaning it's very sensitive to any noise in the input. And so you have to account for that in the inverse problem through this idea of regularization. And a lot of these techniques are really based on smaller problems and direct solvers. They're not really catered to large-scale problems, which you might want to do an iterative solver. And so I'm interested in pushing the frontier on that. And on the third point here, differential equation constraint optimization. So I've been stretching out onto this field here. It's somewhat related to inverse problems. They have a little bit of overlap, but they do have some specific considerations. One of these are a optimized versus discretized, or discretized and optimized approach. Meaning, do you compute gradients first analytically? Do you write out the gradients that you want to compute and then discretize that? Or do you first discretize the optimization problem and then compute the gradient of that? And if so, how are those two things related? Are they consistent? And is it better to do one or the other? And of course, all of that is going to depend on the numerical methods you're using for discretizing. And in particular, I'm interested in leveraging energy or entropy stable discretizations for nonlinear problems. So there's a lot of recent work on, again, this concept of energy or entropy conservation for nonlinear problems, but they haven't really been used in a differential equation constraint optimization setting. So I'm looking into applying those methods in that setting. Top of the outline, I'm going to discuss some of my prior work. The first problem is related to the forward problem, specifically discretization of multipoles. So I'm going to get into that in a moment. The second bullet point is on inverse problems, and the third point is on, it's with regards to differential equation constraint optimization. So moving on to the first, discretization of multiple sources. So I want to focus on this application. This is the setting here is marine seismic survey. So you have this boat that has these array of air guns. These air guns are essentially compressed air canisters that are released and effectively, it's kind of like an underwater explosion. It's very loud and it generates these artificially induced shock waves that then propagate down, interact with the earth, and then you hear the echoes. And you try to get some information from the echoes. Okay, the forward problem. So I'm interested in better modeling this source, this kind of seismic source. So here's some modeling equations. For simplicity, I'm just going to work with the acoustic equations. This is a first order version of the wave equation. That's one way of thinking about it. The P variable here is pressure, V is particle velocity, kappa, and kappa is Volcom modulus, and beta is 1 over density, so buoyancy. And F here is going to represent the air gun source. So here are the air guns. This is a bit of a close-up of a single air gun, and this is what they look like as they're exploding. And the way that these air guns are modeled mathematically are as a point source in space. The dimensions of these air guns are of the order of tens of meters, which is much, much smaller to the waves that are generated, which are the order of 100 meters. And so we can mathematically express that as a point source. And so the simplest point source one can think of is the delta function in space and something in time, some function in time. So you put that onto your wave equation as the right-hand side, and in the simpler case, you could solve for it, and this is the kind of pressure field you get. So notice that as a function of x position, it is spherically symmetric. It only cares about the magnitude of x, it doesn't care about angles. So the resulting is isotropic response, spherically symmetric. This is contradictory to what is actually observed for air gun arrays. Air gun arrays actually demonstrate directivity. Certain directions are stronger than other directions, and so we call this anisotropy. So air gun arrays, this is not a good model for that. Earthquakes as well are another perfect example of seismic sources that are not isotropic. They have anisotropy, meaning depending on the angle you're viewing from, you have different strengths. So what we ended up doing is we modeled then, rather than just using a delta function, we're going to use derivatives of the delta function to account for anisotropy. So here I'm using multi-index notation, so you can think of this as being just partial derivatives of the delta function, and if you were to sum up all of the indices of the vector s, that would give you the order of the derivative that you're taking. So again, we're modeling the seismic anisotropic seismic source still as a point source in space, but now we're going to be able to demonstrate some anisotropy if we include derivatives of the delta function. So just to show you what these things look like, here's a plot of the pressure field at a point in time, so a snapshot in time, x and y axis, or I think I call this x and z axis. And so the plot here is for the monopole case, or the case where you have no derivatives, it's just the delta function. And I forgot to put here a function in time. It's actually a Richter wavelet in time. But you see here, as expected, it's nice and symmetric. Right? According to that formula, nice and symmetric, circular symmetry here. For the case where you have one derivative of the delta function in the x2 direction should be the x-axis here. You see this dipole behavior. This is what we call these multipoles. So dipoles for a first order derivative, multipoles for higher order derivatives. Yes?
So if you have like two derivatives, is that like quadrupoles?
Yes.
Okay.
We call those quadrupoles and then so on and so forth. Yeah. Alright, so we have a way of representing anisotropic point source seismic sources. We're going to stick that into our right-hand side of our PDE, and then we're going to, so particularly I was interested in finite difference discretization. So here I'm just showing you a particular choice. This is called staggered grid finite difference discretization. And that's the discretization of the acoustic equation that I had earlier. But this is for the 1D case, just to simplify the formulas. It's going to be similar for 2D and 3D. They just look more involved because there's more terms involved. So just wrote it in for the 1D case. And so P here, pH, IN is the approximation to the pressure field at the grid point I in space and the nth grid point in time. And these DHs are supposed to represent a discrete version of the derivative. In this case, it's a center difference approximation to a derivative. And so these kinds of approximations are second order in time and 2p order in space if you use a 2p order method in space. But what's highlighted in red is really crucial. What should f of h be? What should be what you plug in into your finite difference discretization if your f to begin with was a delta function or a derivative of a delta function, something that's not defined point-wise, right? What in the heck are you going to do? Are you going to plug in for f? No, f of h here is a grid function, but f is a distribution. So yeah, so what do? How do you discretize f? Not only so that it makes sense in a finite difference setting, but how do you do it in a way that it preserves numerical properties of the method? You want to preserve perhaps this behavior of the numerical method. How would you do that? So that is what the work I did in my PhD, discretization of multiple sources. And the key idea was to mimic the behavior of the derivatives of the delta function as a distribution on polynomials. This is for the general alpha polynomial case. Alpha here is also a multi-index. But just think of this as what if you apply the delta function or its derivative on a linear or quadratic polynomial, so on and so forth. So you should end up something on the right-hand side. And so we want our discrete version, so I'm going to call eta h to be the grid function version or discretization of the derivative of the delta function. And rather than have a integral, I'm going to have a summation over the grid, but still acting on the polynomials here. So I want it to be the same. I want it to give me the same response, but in this sort of discrete version. And you want to do this for enough terms so that if you do it for this many terms, depending on how many derivatives you're taking, then this would result in a Q-order approximation for the S derivative of the delta function. So more derivatives, more terms you need in that. The higher the order, more terms as well. So these are some plots. These are the not just the eta function as a grid function, but the eta function if I were to fill it in and what's going on in between grid points. So as you suspect, the hat function is a reasonable approximation for the delta function. In fact, this is what most people do, not everybody. Just put a hat function. And that is actually a second order approximation to the delta function itself. A fourth order approximation will look like this. So these are piecewise polynomials that satisfy the moment conditions I had earlier on. Here's the derivative. So second order approximation to the monopole, or one derivative on the delta function. That's quite intuitive, right? You would expect sort of monopole behavior. And here's the fourth order approximation to the, again, the monopole. Higher order piecewise polynomial. I didn't include here, but you could do a tensor product to define 2D or 3D multiples as well. So just to give you a summary of the work, generalized moment conditions. So there was some previous work on these moment conditions that were only for 1D. I generalized the work to higher dimensions, and more importantly, I showed some convergence results. And so we really had to be careful of what we meant by convergence. You had a PDE with a singular right-hand side. What is it that you mean when you're saying that your numerical method is converging to the solution of the PDE? And so, given that we're dealing with distributions, we really have to talk about weak convergence and not convergence in a point-wise sense. And so we developed this concept of weak convergence, and we showed, for some cases, convergence. The rates of convergence were suboptimal, and we conjecture better results given some of the numerical results we observed. And we actually did this for quite a large family of hyperbolic PDEs. So that was our contribution. Numerical results show degradation of convergence rates if proper singular source approximation is not used. So if you're not careful, you might be degrading the numerical method. If you just use, for example, the hat function for everything, but you really wanted a higher order method. All right, so that was just a forward problem, an example of me really going in and identifying and modeling, and also how do you solve this numerically. So now that we have a way of modeling these multiple sources, can we invert for them? Specifically, I'm interested in recovering the time component of the multiple. I'm going to assume I know the location, but I want to know what is the time component. And this might be useful in earthquake seismology, if you want to know something about the temporal evolution of the earthquake, or in the exploration seismology case, that might be an important thing to know, even within the regular inverse problem of recovering median parameters. So the source parameters W, functions of time, is what we're interested in recovering. The forward problem is, given W, simulate the data vector D. So D is the pressure field at certain points in space and time. P is solution of acoustic waves. So we can express this forward problem through this forward map F. F acting on W gives you D. F is actually a linear mapping. One could show it's a linear mapping, and in fact it's really nothing more than a convolution, multi-channel convolution, but a convolution nonetheless. So the inverse problem, we write it as a least squares problem, and so we want to find W that minimizes the data misfit between predicted data and observed data. And so this is a least squares problem where F is linear, and so I could write, the solution to this is the solution to these normal equations. Well, it turns out that these normal equations are ill-conditioned, very ill-conditioned due to the singularity of the multipoles. There's a connection, and so the connection is the condition number of F transpose F is of order W max. W here is the frequency of the temporal component to the power of 2 m star. M star is the order of the multiple. So the more multiples you have in the way you represent your source, the more ill-conditioned this is, and it's exponentially with regards to the multiple order. And so there's been prior work that has looked at how do you address this ill-conditioning when you do the inverse problem, when you try to solve the inverse problem, in the context of multipole representations. And one idea is, which is really if you can, improve your data coverage. If you have better data, you're going to better condition the problem. So that's a bit of a no-brainer. But you might sort of be constrained by what you can do in terms of the engineering if you can get better data. The second thing you can do is simplify the source model. If you simplify the source model, then the problem is better conditioned. True, but then you lose all the anisotropy that you wanted to account for. So that's not something that we want to aim for. And the third thing is really the traditional thing that you might want to do, take an off regularization. You regularize the least squares problem, and you do that, and that should help out. And it does. But there's a fourth thing, which is what we did. My approach was we're going to modify the problem so that the norm associated with the data misfit modified inner product of source parameter space to yield better bounded operator F. So that's a very mathy way of saying I'm going to use a preconditioner to accelerate the iterative problem for solving the normal equation. So I'm going to add a weight to the inner product. So here's the inner product in the source space for the W's. I'm going to weight it by this operator L transpose L, such that if you take the norm of W with respect to this weighted norm, it's roughly equal to the norm of FW. So L is kind of like a pseudo solution to F. That's one way of thinking of preconditioners. It almost solves the problem. So it should accelerate then what I'll do after that. So equivalent to a preconditioner for the normal equations, preconditioning by a matrix M, and M would be L transpose L inverse. So that's the general idea. We want to introduce this preconditioner. And so then you would ask, well, what should L be? You have a general idea what you want it to be, but specifically, what is it? So this was quite an interesting result that we observed. So L is going to be the diagonal operator, and it's basically nothing more than temporal derivatives of certain order, scaled by 1 over the velocity, depending on the multiple order. Now, you're going to need more derivatives if you're involving more multiples. If it's a higher order multiple, you're going to need more derivatives to sort of undo what the multiple is doing. But then there's this extra gamma constant that is depending on the dimension you're in, which is very interesting. So we arrived at this formula. So again, you can think of this as being the inverse of this would be a inverse of the forward map. So you can think of this as being roughly the forward map. So what we observed when we analytically computed some of these solutions in a simpler case, we saw that the pressure field looked like derivatives of the input function W. Derivatives of a certain order. We observed that you started out with 0 derivatives, then 1 derivative, 2 derivative, and you would tack on derivatives depending on the multiple order, and then you had an extra derivative in 3D. But in 2D, it was giving us something weird. It didn't look like 1D or 3D. And so, you might be wondering, well, how are you getting fractional derivatives? Where's that coming from? So, let me give you an example of what the L's are going to be, and now I'm going to show you a plot that should motivate why we ended up with fractional derivatives. So here's a function f. Let's say you have a monopole term and 2 dipole terms. And so this is in 2D. Your gamma should be 1/2 according to this formula. Your L1 associated with the monopole should be just a half derivative. And your L3 and L2 associated with the dipole should be 1 over c. Again, you scale by c depending on the monopole order or the multiple order. And 1/2 plus 1 because of it's a dipole. So 3/2 derivative. That's the formula, but let me show you this visually to convince you that these are fractional derivatives. So on the left column, I'm showing you a plot of the pressure field for the monopole case. So here is the pressure field if you have some Ricker wavelet. This is what you would observe. Here's the pressure field for the dipole case. Okay, extra wiggles. Here's the W, so the Ricker wavelet, and I took a fractional half derivative. Aside from an issue of scaling, right, so the scale is not quite right, but the general waveform is there. Same thing for the monopole case. So here's a 3/2 derivative of the Ricker wavelet. Again, aside from scaling and perhaps a little bit of a time shift, the waveform overall is similar. And if you look at the formulas, they look like fractional derivatives. So fractional derivatives, I'm not sure if I go into too much detail, I don't. So fractional derivatives are integral differentiable or integral differential operators. It's basically integrals and derivatives involved in this operator. That's how you could define a fractional derivative. But if you're interested in that, I'm not sure if I have slides on that. But anyways, okay, so I want to get to an example here. Here's a simple 2D diagram. I'm assuming that my source is here and my receivers are here. Okay, I'm going to attempt to recover the W's, the multiple coefficients, functions of time. And here's I have some subsurface feature. There's a salt dome underneath just to make things more interesting. I'm not doing just a homogeneous medium because that would be a little too easy. Here's a plot of the log of the data misfit, R. R is the difference between observed data minus the predicted data for a current approximation of my recovered W. Again, the W is just what I want to recover from the data. And I'm using here conjugate gradient. Since this problem is a least squares problem, I can use conjugate gradient. So if I do this, this is the misfit, so we want the misfit to go down as a function of iteration k. In dashed, this is dotted. In dotted, we have just regular conjugate gradient least squares. And it's quite slow. It's struggling because this problem is ill-conditioned. And with this preconditioning that I suggested, in dashed is just preconditioning, and in dashed plus reg means regularization, so some Tikhonov regularization is added as well. So in both cases, we see that we accelerate, and we get to a smaller data misfit than without preconditioning. So as funky as that preconditioner was, it's working in this 2D case. And just to convince you that not only did we get a smaller data misfit, but yeah, so this is just a qualitative look at the data, matching the data. So in black is the noisy data, the true data, observed data, and in blue is what you recovered with regular conjugate gradient after 150 iterations. So not very good in certain places, and after 6 iterations, the preconditioned conjugate gradient method. So a lot better than the blue curve, which is just to demonstrate that we are doing a pretty good job in fitting the data. And this plot here this is for a different problem, evolution of inversion error, and this is to highlight the importance of regularization. So again, without preconditioning, you effectively are stalling out, you're not getting anywhere. With preconditioning, you accelerate. But for this harder problem, oh, actually I know what we're doing here. So here we're plotting the error to the inverse, so the inversion error. This is not the data misfit, this is the inversion error. So yeah, you're doing a better job at fitting the data, but also you want to make sure that you're doing a better job in getting to the true solution. Right? In this case, we're doing the true solution, so we can produce these plots. So these plots demonstrate that regularization helps make the inverse process a bit more robust with respect to iteration. So it's still a benefit to look into regularization. How are we on time? Okay. Subvariable multiple source inverse problem. It's a very hard problem. It's ill-conditioned. We develop a preconditioning strategy to accelerate the conjugate gradient. And these preconditioners are, this is the word I was looking for, differential integral operators. Or fractional derivatives if you're in 2D. But if you're in 1D or 3D, these are just regular derivatives, or just integrals being the inversely derivative. Computational costs, okay, you accelerated conjugate gradient with this preconditioner, but at what cost, right? How much did it cost for you to apply the preconditioner per iteration? Are you truly saving costs at the end of the day? So the number of multiple terms is much less than the number of receivers in the data. And the cost of preconditioner is actually related to the number of multiples, and therefore multiple terms, and therefore this is going to be much smaller than the cost of the forward map, which is related to the number of receivers in the data. So it's negligible. So yeah, 60 preconditioning steps is a lot less than 150 non-preconditioned steps, but even computational cost twice, it is a lot less work. All right, so the last bit of work is on discrete adjoint computations for relaxation Runge-Kutta methods. So I was hinting at this earlier. Linear wave equation propagation. So energy stability was important for methods that are for problems that are energy conservative, right, or energy stable. You want the numerical scheme to perhaps also mimic that. And if you have that, especially for those of you that do Hamilton-Jacobi equations, you want to evolve these solutions for long periods in time. And so a energy conservative or stable method will help you in, will be great for that. In the nonlinear case, the concept of energy stability generalizes to entropy stability. So this is just a more general way of thinking of that. Nonlinear problems are interesting because they model complex phenomena like shock formation. And it is a challenge to design methods that are entropy stable all the way through in time and space. Here's an example of solutions to the nonlinear pendulum problem. In blue is the method known as relaxation Runge-Kutta, which is an entropy stable method. Entropy stable with respect to the specific problem. And so this is the phase diagram. We expect a nice cyclical phase diagram. If you use regular Runge-Kutta form, which is the sort of first thing you do if you want to solve something in time in ODE, it is not entropy stable, and so the price you pay is that your numerical solution is actually decaying in a way that is not physically relevant. And so that can be attributed to the fact that your Runge-Kutta scheme is not entropy conservative, and in fact this plot here is a plot of time versus entropy conservation, you see that there is a non-zero, substantial non-zero entropy for this problem, as opposed to the relaxation Runge-Kutta, which is effectively zero in these computations. So yeah, when solving these problems, you want to be entropy stable. So relaxation Runge-Kutta methods preserve discrete entropy balance given entropy functional. This is work by Hutchinson and Ranosha. So I'm interested in applying these kinds of methods in an optimal control setting. So specifically, I need to compute derivatives or adjoint formulas for these relaxation Runge-Kuttas. So again, back to optimal control, we have a functional we want to minimize. We have a state equation we want to solve. Let's suppose your state equation is a first order ODE, system of ODEs. For simplicity, that your control variable is the initial condition. So yeah, so there's a state equation, and you would solve that by Runge-Kutta or wherever. So actually, I could rewrite this problem. I could eliminate the constraint by defining this mapping between u and the state variable y through the solution of the state equation. The adjoint state method computes gradients to this. Oh, okay, I have a wrong letter here. This j should be c's. So j's and c's. So the gradient of this objective function, which is what you would want to compute if you want to use any sort of gradient-based method like steepest descent, or if you're really fancy, Newton's method. If you want to compute those gradients, well, you're gonna have to do it implicitly through this mapping. So there's a bit of implicit differentiation, but effectively, the adjoint state method gives you the gradient, again, j's or c's, by the solution lambda of a related problem referred to as the adjoint state equation. This is quite standard in optimal control and inverse problems, but effectively you can think of it as, okay, I have an objective function, I want to compute its gradient, I need to compute these things, this is the gradient, and I need to solve a related adjoint problem. So this is just another differential equation associated with the original differential equation. So in a discretizing optimist approach, E is the matrix operator related to the initial value problem discretization. A discrete adjoint of a test-setting scheme is then related to this operator here. And so here I'm taking a discretized then optimized approach. So what is the gradient of this operator if it's related to the Runge-Kutta discretization or relaxed Runge-Kutta discretization? Properties of adjoint Runge-Kuttas. So this has already been shown in the past. The adjoint Runge-Kutta method is, so if you had this problem and you did the adjoint of a Runge-Kutta, that solution would be consistent to if you applied a Runge-Kutta scheme to the adjoint problem. There's that consistency. And moreover, the adjoint Runge-Kutta is really an S-stage order R Runge-Kutta if the original forward Runge-Kutta is also S-stage order R. Okay, so entropy is functional, it generalizes energy. We say a problem is entropy stable if the entropy is not increasing as a function of time. It's conservative if the entropy is constant. This is the discrete version of that. As you're stepping forward in time, are you decreasing entropy or are you conserving entropy? So relaxation Runge-Kutta preserves entropy stability or conservation of the continuous problem. And so it does this by modifying the regular Runge-Kutta method with this gamma, this relaxation parameter. So all the other stuff is as normal, but this gamma relaxation parameter is computed by solving this nonlinear root problem. So here's the root equation. So you set this equal to 0 and try to find gamma for which this is equal to 0. And the developers of this method showed that you could do this by a simple bisection method, and it's a well-posed bisection problem, and it all works out, so you can compute this. And that gives you the gamma, and then your solution at the next time step is interpreted as the solution not at the next time, but at this sort of scaled time step by gamma. So relaxation Runge-Kutta preserves entropy stability. and it preserves order of the baseline Runge-Kutta method. And what I did is I developed the adjoint formula. So gamma, lambda here are the internal stages, and the lowercase lambda are the adjoint states that you're computing for. And this, what's in red is what's different. If you didn't have that gamma, then you wouldn't have the stuff in red, and this would be what you would normally have for a typical adjoint Runge-Kutta scheme. But the red stuff is what's new for relaxation Runge-Kutta. It's a lot of formulas here, but they involve some implicit differentiation, which was key in defining those formulas. I want to get to an example. Here's a cost functional for the pendulum problem. So this is the pendulum problem. It is energy conservative with respect to this. Oh, sorry, no. This is a cost functional we're going to minimize. This is the problem. Here's the initial condition. This is the entropy that the nonlinear pendulum problem conserves. So we want to make sure that our discrete problem is conservative in that sense. So we want to compute gradients to this problem. This is the adjoint problem associated with the nonlinear pendulum. And so we're going to study the convergence of our adjoint solutions at the initial time. And so these are just some quick convergence plots. Just demonstrating two things. Demonstrating that the relaxation Runge-Kutta, the adjoints of these things, are consistent, they are converging, and they're converging with optimal rate to the regular adjoint Runge-Kutta. And moreover, they are more accurate. So they're further down. The blue curve is the relaxation Runge-Kutta stuff. That's further down, so it's more accurate than if you were just to try to solve these adjoint problems with traditional Runge-Kutta. Just to drive home this accuracy, in blue is the relaxation Runge-Kutta. This is a plot of the norm of the adjoint solution as a function of time. And so it's a bit oscillatory, and it grows a little bit. But if you use the wrong method, if you do the adjoint in the wrong way, which is this other in red and in red and black and in magenta, then the adjoint solution is actually pretty bad, especially this black curve here. You see some blowing up of the adjoint solution, which is not very good. So in summary, we derived discrete adjoint relaxation formulas. We demonstrated, at least numerically, that these methods are consistent, optimal convergence order. I didn't have results on this presentation on this, but they also satisfy a time symmetry property, which is important in some contexts. And future work, implementing multiple sources. What if we did a joint source medium inverse problem, earthquake seismology applications, further challenges in large-scale ill-condition inverse problem, and further work on adjoint relaxation and that kind of stuff. All right, yeah, that's all I had. Thank you.
Thanks for a great talk, and we have time for questions now.
Yes.
Roger.
I have a question about your nonlinear pendulum.
Oh, yes.
Can you tell me how to make one?
Oh, no. That's why I became a mathematician. I don't have to do physical things. Yeah.
Because I'm all about doing stuff in the lab.
So the nonlinear pendulum is, so when you think of the pendulum equations, if you go through a physics class, they linearize the problem and you end up with this nice linear, ODE that you can solve. And so really what they mean by linear versus nonlinear is you have small swings. So if you stick with small swings, you're in the linear case. If you go to crazier swings, you're in the nonlinear case. So really you have a nonlinear pendulum, you just got to swing it more.
Okay. So every pendulum is nonlinear, you just have to swing it harder.
Yeah. You just gotta swing it harder.
That's more than 5 degrees.
Yeah.
That's when the sine alpha equals tangent alpha approximation breaks down.
Yep.
Thank you.
I didn't quite get the derivative of delta functions. Like I taught my students in my imaging classes, the delta function gives an example, a testing function, and make it infinity high and infinity c.
Yeah.
Because I mean, if you take the derivative of delta function, it's basically you get 0 in one function or the
Well,
So
you,
what do you mean
Yes.
here in this context?
so the delta function, and this is one of my biggest pet peeve is the name delta function. It's a misnomer. It's not a function. It's not something we can define point-wise.
Yeah, I know.
But it's, for visual purposes, that's what we say, and it's, there's a reason why we sort of have that visualization, because you could also define it as a limit of convolutions with a bump function that increases to infinity. So if you get away from the concept of defining this as a function, and you think of it as a distribution or an operator, then you could think of the derivative, the action of a derivative in a distribution sense. So this is basically, what I'm hinting at is weak derivatives. So the concept of a derivative, but for distributions. Now that would be how you make sense of derivatives for the delta function. And so the idea is you do integration by parts to move the derivative on the delta to the test function. And then you apply the delta function on the derivative of the test function. That gives you the action of the derivative of the delta function.
Because the idea was for you to model something that's not a point, like, that's what
Still,
you move
yeah,
on.
we wanted something that was point-like in space, but not isotropic in response for the pressure field. And like, if you stick it to the wave equation, we didn't want something that gave me as an answer
Okay.
a wave, a spherical wave. I wanted something more complicated. And so this derivatives gave us some anisotropy.
So, yeah, still kind of having a problem with what
Yeah.
does that actually mean, what was derivative of the delta? It's not the derivative even of the distribution, is it? Like,
Yeah.
I mean, how will you take the, because let's say you take a Gaussian, you can put a parameter, go to 0 and you make it, infinitely long, infinitely narrow and long. And keeping preserving area. Now in delta function, you preserve area to be 1. That's the whole idea.
Yeah.
The properties of the delta function.
So if you define the delta function as a pairing, we write it in integral form, but we really mean a pairing between a function and the distribution. Right? And for the derivative, let's say this. What you would do is you would do integration by parts, move the derivative to the f term. So really this would be, I forget if there's a minus. It's probably a minus. So this would be the definition of the derivative of the delta function, a minus and a derivative on the test function. And you could generalize this to more derivatives in higher dimensions.
Yeah, you do it, differentiate by parts and move the derivative over to the f. That's then the second term in the integration by parts trick. That's
Yeah.
where you pick up the minus sign and the surface term goes away.
Because you assume that the function is of compact support, and so as you go to infinity, or at least you assume that in the limit of infinity, then it goes to 0.
By the way, so there's a Jackson problem in one of the, so Jackson E&M, where they actually have, it's a radiation field from sources that basically have first and second derivatives of the delta function. Like, it's a nasty problem.
There you
No,
go.
Rory, you know what I'm talking about? Yeah. But Sergio, you had a,
So you mentioned the fractional derivative.
Yeah.
As I know, fractional derivative analysis is a very tough task in mathematics. I remember Caputo
Yes.
name. It's very fundamental. You change everything in fundamental mathematics. Have you used those ideas? By the secret, I published around 5 or 10 papers on fractional black holes, fractional analysis, Friedman, Caputo, fractional Perelman-Ricci flow theory. That's why I put the idea, because you develop Runge-Kutta method, numerical, it's okay.
Yeah.
But it seems to me you are using a standard differential and integral analysis. But you try to plot with fractional things. It should be a different mathematics fundamental.
Yeah, so for this business of fractional derivatives, we were basically looking at analytical solutions, and they involved I forget the exact formula because it's
Yeah, okay, I understand there are a lot of formulas and fractional.
Yeah, but
Different approaches, and they contradict each other.
Yeah.
For instance, the fractional derivative of a constant
Yes.
in the Caputo approach
Yes.
is zero.
Yes.
But there are fractional calculus when
Yeah.
you take the derivative of a constant, it is not zero.
yeah. So we base our this whole stuff on fractional derivative because we ended up with something like this, and so we thought, well, that looks like one of the fractional derivatives we've seen floating around, and so the way we defined the discrete version, because these are discrete things, is through, there's a finite difference sort of formula for fractional derivatives. I forget the name.
Yes, there are infinite numbers.
Yeah.
For me,
Yeah.
it was important only to work with that calculus,
Okay.
which take your fractional derivative of a constant to be zero.
Oh, okay.
Because if not, you miss everything.
Yeah. So what we assume is that our the things we're taking fractional derivatives of, we assume that they have they're causal, so they're zero before some initial time. So I think that zeroes out some of the floating around constants with these derivatives, these fractional derivatives. So something like this Ricker wavelet.
I saw such at a
Yeah.
conference 10 years in Turkey. They published multi-volumes on fractional calculus. It's a fight in mathematics, how to define it and so
Yeah,
on.
just definitions.
And then applications in physics, for instance, to elaborate Lagrange
Yeah.
calculus.
Yeah.
Because why I put these questions? Because
Yeah.
we use concepts as entropy and
Entropy.
so blah, blah, blah. But if you work with a fractional
Yeah.
calculus, it's something very different.
Something, yeah. But what was miraculous was that using that finite difference formula for the fractional derivative, we get those curves on the right.
Okay.
That look like the curves from the left that, again, the curves on the left are solutions to the wave equation with multipoles. And so that's what we wanted. We wanted to see that they look the same, or at least in waveform.
Okay.
That was the motivation. And so, given that particular definition, it worked for us. And I didn't look too hard, to be honest, in terms of all the many, possible definitions. I looked at the one that was easiest in terms of numerical implementation, and that it was giving us something consistent what we were observing with the wave equation. But yeah, no, it's very interesting stuff, and there's more applications beyond, what I'm doing, for sure. And
Yes, I'll apologize if I missed this because I got here a little late, but with these seismic applications, you mentioned that there were many fewer sensors than points that you're interested in reconstructing, I would say.
Okay.
And I'm just wondering, for ballpark figures, what kinds of numbers of sensors are we looking at, and how many points are you looking to reconstruct?
Well, they do have large number of sensors. It's where did I say small number of stuff? I might have said
Well, there's
at this point. Oh, I was referring.
yeah.
Yeah. So at this point, I was referring to the number of multiple terms. So in theory, there's a paper that my PhD advisor actually wrote on these multipoles that any sort of point-like in space anisotropic source can be represented as a series of multipoles like this, multiple series. Obviously, we'd like to, in practice, you truncate a series, right? And so you're going to truncate that number to be quite a small number, and due to the physics of things, the higher order multipoles tend to carry less energy because it's quite, you need a lot of energy to really excite some of the higher multiple stuff. So really it's the lower order stuff. It's kind of like a Fourier series in that the lower order terms, there's a sort of exponential decay of the coefficient.
If you knew those higher order multiples, it wouldn't tell you anything more anyway.
Exactly. So so the idea is that you really need a few number of multiples. The number of multiples you need is roughly related to the cost of the preconditioner. Because there's so many, much less than the number of receivers. The number of receivers is to the thousands.
Okay.
These are like large nets in the ocean.
Okay.
Because they really want to get as much data as they can. Once they make an explosion and they're recording these things.
So this is basically maybe mineral exploration or oil exploration?
Yeah.
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 Mhm.
But like, you know, they spend millions in getting this data and
Yeah.
plugging these boats, and these boats are enormous, and they have other little boats, you know, making sure that the arrays are out and all these things. Never been, but I've
Humpback
heard.
whales are saying, what the hell was that?
And then I always get this question, which it depends on the audience, but what the question I normally get when I talk about this seismic exploration stuff is environmental stuff, right? These are underwater explosions that you're sort of setting off to, you know, get information. Yeah, no, it affects whales, dolphins, and then try to do things to, you know, mitigate, to, you know, they try to scare off the animals so that they're not around when the big explosions go off, but, you know, that's oil and gas. That's the business, I suppose.
Well, in Virginia, they used to go fishing by taking dynamite and throwing it in the water.
Yeah.
And then the fish float up.
Yeah.
That's environmental.
Yeah.
So the sonic thing they towed behind, you said it was on the order of 10 meters?
Yeah. So these are quite small.
Well, that seems huge, but I guess compared to the wavelength, you said, 100, okay.
Yeah, no, these are seismic sized wavelengths that they're generating.
Okay.
Okay.
Yes, that's why they're, you know, for all the mathematical purposes, we model this via a point source.
So any other questions, comments? No. Okay, well, if not, let's thank Dr. Bencomo again. As always, donuts left over, and if you want to ask more questions, feel free to filter off glass.